Welcome to The Explainer. Today, we're diving into something truly incredible, all based on the fantastic research of Dr. Sudheendra S G. We're talking about ray tracing. If you're a 3D creator, a student, or a professional in the media industry, this one is for you. We're going to uncover the amazing story of how a little bit of impossible math became the real-time art that's literally at your fingertips right now.
All right, let's just start with a number because it kind of sets the stage for this whole thing. 1 quadrillion. That's a 1 with 15 zeros after it. That's how many calculations a computer might have to make to render just one single second of a modern animated movie.
I mean, to really wrap your head around that, imagine if every single person on Earth, all 8 billion of us, worked together nonstop for 12 straight days. That's what it would take to create just one frame. This was the monumental, almost absurd challenge that artists and engineers were staring at for decades. It was pure science fiction.
So why? Why does making these beautiful, realistic images need that much brainpower from a computer? And, more importantly, how did we finally crack the code and move this technology from giant supercomputers onto the desk of a regular creator?
Well, the secret is this algorithm called path tracing. It's pretty much the gold standard because it does an amazing job of simulating the actual physics of light. But, and this is a big but, for 30 years, the cost of doing that was so high that it was basically locked away, only usable by companies with huge, expensive server farms.
And you can really see this when you look at the timeline. The idea for this stuff existed all the way back in 1986. But it took 3 full decades before movies could actually use it. And even then, for a film like Moana, it was this Herculean effort that took months of rendering time on thousands of computers.
Okay, so here's the fundamental problem. A light source, like the sun, it shoots out a practically infinite number of light rays. There is just no way to calculate all of them. So, how did computer scientists cheat? How did they get around this basic law of physics? This is the brilliant part. They just completely flipped the problem on its head. Instead of trying to track a bazillion rays coming from the sun, most of which would just fly off into space and never hit our camera anyway, path tracing does the opposite. It traces a manageable number of rays backward, starting from the camera and going out into the scene. It's genius, because it means every single calculation actually matters for the final image.
And this whole process happens in a few key steps, over and over, thousands of times for every single pixel on your screen. A primary ray shoots out and finds an object. Then shadow rays check to see if it's in direct light. After that, secondary rays bounce all over the place, picking up that soft color-tinted light from other surfaces nearby. You put it all together, and that's what we call global illumination. That's the secret to making things look real.
Okay, but shooting out a ray is really only half the story. Because as soon as that ray leaves the camera, it enters a world that isn't made of solid things. Nope. It's made of millions, sometimes even billions, of tiny little triangles.
I mean, just take a look at a really complex scene, right? Like a super detailed barbershop. A scene like that can easily be made of more than 8 million individual triangles. That is a massive digital forest for a tiny little ray to get lost in.
And boom, that leads us to the next impossible problem. For every single one of those billions of rays, how does the computer find the one specific triangle it's supposed to hit? Checking all 8 million of them for every ray, every time? No way. Any computer on Earth would just grind to a halt.
The solution here is another piece of pure genius. It's an algorithm called a bounding volume hierarchy, or a BVH. The easiest way to think about it is like a GPS for light rays. It basically takes all those messy triangles and organizes them into a neat tree of nested boxes, going from really big boxes down to smaller and smaller ones. And by doing that, the BVH takes this impossible search through millions of triangles and turns it into just a few simple steps. The ray just asks, which big box am I in? Okay, now which smaller box inside that one? And so on, until it's only got a handful of triangles left to check. It is unbelievably efficient. So now we've got these really clever algorithms, but even the smartest math still needs raw, brute force power to actually handle billions of these rays. And this is where the hardware, and maybe a little bit of foresight, completely changed the game.
Yeah, this is where vision really meets the hardware. Way before ray tracing was a buzzword, you had visionaries like Steve Jobs at Pixar. And he wasn't just obsessed with technology, he was obsessed with story. He knew that to tell bigger, more amazing stories, they needed computing power that just didn't exist yet. So he pushed for it. helping to drive the creation of the very machines that rendered those early Pixar films. He basically proved that great art needs great power, and that set the stage for the hardware revolution that was coming. And that relentless push for more power led to this. I mean, just look at this comparison. It's absolutely mind-blowing. A modern GPU, something that fits in a shoebox, is almost 3 times more powerful than the fastest supercomputer in the world back in the year 2000. A machine that cost over $100 million and took up the space of 2 basketball courts.
The real breakthrough is the specialized hardware that's now inside these GPUs. They're called ray tracing cores, or RT cores, and these things are purpose-built little engines designed to do just 2 things, but do them at lightning speed: navigate that BVH tree we talked about, and calculate that final ray triangle hit. Because they're so specialized, they can process billions of rays every single second.
And all of this, it brings us to today, the final and I think the most exciting chapter in this story. Because this technology, which was once impossible, isn't just for Hollywood anymore. Thanks to all this innovation, it's now in the hands of artists, creators, and students everywhere. If you're a 3D creator, this stuff is now in the tools you use every single day. Game engines like Unreal with its Lumen system, which gives you real-time global illumination. Animation software like Blender, which uses path tracing right in its core engine. Even games like Cyberpunk use these techniques for incredible reflections. This is all happening on a standard PC. It's amazing. So the next time you see a perfect glassy reflection or a really soft, realistic shadow in a game or animation, just remember what you're actually looking at. It's not just one thing. It's this beautiful marriage of physics, some really clever math, and hardware that's powerful enough to make it all happen in the blink of an eye. And that really just leaves us with one final and pretty exciting thought. This level of creative power, it used to belong in a government lab. It used to require a nation's budget, and now it's sitting right there on your desk. The question isn't, can we do it anymore? The only question left is, what are you going to create with it?